and kind of distance, which are two different things, as we know, aren't they? Yes. If we differentiate this function, we get the velocity function with respect to time. So if you differentiate going this way, and if you differentiate this one, you get the acceleration, so the change of the change. So the rate that the displacement changes with respect to time is the velocity, and the rate of the velocity change with respect to time is acceleration.
What about jerk, snap, crack, pop?
I don't know what you're talking about. Okay. So this is another one of those things that some of you will, one or two you might use in your IA. Be quiet. You might use in your IA, but that is the general principle. Most of us have done that in physics. So how does that apply to a question? We're going to dive kind of into the middle of the questions to start off with. It's already written on the board.
Literally dive. Literally dive. Wait.
No.
I read dive somewhere.
No, it's not dive. Okay. All right. So remember, just a couple of things. The difference between displacement and distance. If something moves out this way and back to the place where it starts, what's its displacement? Zero. But its distance is all that motion. It's all that distance is covered. Yes. So that's the difference. Okay. So we have this question. A particle moves in a straight line, position relative to some zero or origin. And it's given a function. So this particle has this function. So you're going to be dealing with functions every time, obviously. Otherwise, we won't be able to do any calculus with it. Plus 6t squared, plus 9t, plus. Oh, I have a couple of pluses where there should be minuses. That's a minus, and I can't read that. That's also a minus. Okay. So that function, if you were to imagine it, looks cubic. Looks a bit like that, doesn't it? Yeah. Okay. All right, for the time t greater. Okay, so find the expression for the particle's velocity and acceleration. We're just going to find the expression. We'll maybe think about the sign diagrams in a second. Because with all these questions, you can, if you have the displacement, you can just differentiate. You're going back to differentiating now, which is, so the derivative of this function is going to be, what? Yeah, that one.
Well, that's so much nicer.
Yep. And the acceleration function then is going to be this derived again. 6t minus 12. Okay. So we already know, we can start to think about the velocity of the function. Maybe over time, the velocity function is not constant. It is clearly changing, isn't it? It's got so this has got this shape, this has got this shape, and this has got this shape. Yeah? Okay. All right, so find the initial, we're going to come back to the sign diagrams in a second. A key thing here is something called initial conditions. What does that mean?
The starting conditions?
Yeah, so initial or starting condition, yeah, perfect, yeah. Somebody said I don't know, and the answer, that's good, yeah. What do I do to find initial conditions? What do I, sub in what? Zero for t, yes. So initial conditions, we're talking when the time is nothing. When we're just starting off, we're just looking at it for the very first time. This is the picture we're looking at. What is its initial displacement? So s with 0 gives -1. What does that mean?
-1 displacement.
-1 centimeters.
So
Whatever.
yeah, everything is relative to this O, this starting position. And it's actually starting to the left 1 unit. Yeah. Okay. All right. So what's v? When v is 0, we get what? 9. I think that one's self-explanatory. It's going 9 meters per second in which direction?
Positive, so to the right.
It's going that way. Yeah. Positive will be that way. Negative that way. So it's starting off going this way at 9 meters per second. And it's got an acceleration of what? Negative 12. Now, I haven't put... Slowing down. It's slowing down. Okay? So that's its initial conditions. Now, you probably should... these should all be in units. you probably would write this 1 meter to the left of the origin, or wherever. This is 9 meters per second, and this.
Well, we
Oh, is it all centimeters?
-1.
Yeah, we
In
write
physics.
this as a negative one.
In physics, what class were we in?
Math, which
That
also
doesn't matter.
writes
We're fine.
to the -1.
Yes, it should be.
This probably would be discussed.
Yes.
IB terminology.
Yes, it is correct.
Now that's just counterintuitive.
What have I done? No. You've confused me.
It's just CFS -1.
Yes. What did I put? What did I put?
You put CFS
Over F.
Oh. Okay.
This is all supposed to be accurate.
Yeah, I'm stopping with not like that.
What
Okay.
about MS -2 for acceleration?
We need the units.
Oh, still right. All right. This is. I shouldn't have put in the units. Already causing problems. All right. Right. Let's go to part C. I'm deliberately leaving out part A, but let's go to part C. Find the position of the particle when it changes direction.
Find where it's zero.
What or
Where
what's zero?
acceleration is zero. No speed.
No, where
Speed is
velocity is zero.
Find
Yeah,
the zero of the velocity, so make the quadratic equal zero.
Oh my
Okay.
God, intercept x.
So we're trying to find where the particle changes direction. So it has to, in order for it to change direction, this speed has got to start being a negative number. It's got to be zero and then turn negative. So it's like when you throw up a pen, there's a instantaneous motion or instantaneous point where the velocity is zero and then it comes back down in a different direction, yeah? No. Okay, so your idea was to look at the velocity function and find, what was it again?
T.
So we're looking at this function and find out where this is zero, where that instantaneous point. Okay. So I could divide everything by 3 here, I think. Make it easier for myself. Minus 4t plus 3. What 2 times is the velocity 0?
3 and 1.
3 and 1, they both, so t is 1 second, and after time 3 seconds, the velocity is 0. What does that tell us as well, though? It stops twice. It means it's changed directions. Looks like it changed directions twice.
That's really
Maybe it bounced.
Oh, yeah.
Which would make sense from this as our displacement, and even if you look at the velocity of the function,
That's a really funky particle.
that's an interesting particle. We're looking at these two times. So the velocity is negative underneath here, isn't it? Aren't these all negative velocities? And then there's all positive velocities again. So it's positive velocities, then negative velocities, then positive velocities again.
That's pretty cool.
When I graph, okay, so it's important that we recognize what this graph is showing. This is the graph of all velocities of the function. This function gives all the velocities throughout its motion. So I'll put it in more accurately. T1 and T3, it's a U-shaped graph. It crosses at 9 here, didn't it? It's something like this. It definitely dips down below and comes back up. Okay, so if I know a time, I can just plot the time and it'll give me the velocity at that particular point. So if it's 1.8 seconds, I just sub in 1.8 and it'll give me the velocity. So we know that between 1 second and 3 seconds, the velocities were all negative. It was going that way. Okay? And then it turns around. So it's going this way, that way, and then that way. It's done something like that.
What if it's coming towards
We don't know how far it's gone that way. We don't know how far it's come back, but that's got to do with the. Oh, I haven't even looked at it. I'm just talking about the velocity in general. Okay. Draw. Oh, that is a motion diagram. Yes. Okay, I didn't see that coming. Draw a motion diagram. So we're in the middle of drawing a motion diagram. Where does it turn? It starts off at -1. Where does it turn for that first time?
If you
1 second. How do you know that? Oh, at 1 second. But like how? Like as in what distance or displacement? From
sub 1 is the equation. Displacement function.
yes.
Sir, don't you always because you're deriving a cubic and you get it quadratic, so you always get two answers. So if
Yeah.
you do this, don't you always get some? Oh no, because you can have a repeated root.
Yeah, you can have a pre-root, but you're not always going to get a. You're not always going to get a nice cubic equation. More than likely, you're going to get some weird-looking thing with an exponential in it and logs in it or something for real motion.
No, can't you just set it t equals 2?
Well, no, it's T because after 2 it's gone backwards.
No, that 2.
2 is here. This is 1. This is 3. So if I sub in 1, I'll find out on the other graph what the displacement is at that point. On this graph, I'll find out what the displacement. Or I can just sub it into the function and get what it is.
Is that an acceleration?
Nope.
Oh.
That is velocity.
Oh,
That's
I
all
thought
velocity.
I thought the 9 was an A.
No, that's the 9. This is referring to this 9.
Oh.
Okay. All right, so what is this displacement when it turns around for the first time? Did anyone sub in 1? Someone did. Bode.
1 minus 6 plus 9 minus 1.
Okay. So S with 1 in it is 1 minus 6 plus 9 minus 1, which is 3. So that means 1, 2, 3. That's our turnaround point, isn't it? So it's coming back. Okay, it's coming back. How far back does it go? Does it go back to where it started?
To 3.
So you got to sub in 3. So S with 3 in it. A bit more difficult now. I think is 27 minus.
36, 30, 34. What? 54.
You're saying words. You're not thinking. 27 again minus 1. Well, that's nice, isn't it? Where does it go back? It goes back right to the place where it started. Doesn't it?
Yes.
Am I right? Yeah. So it goes all the way. It goes all the way back to here. So its displacement at that point is nothing, isn't it? And then what?
How does it just instantly teleport back to where it's?
It's not.
It's not like 2 seconds.
Just imagine it's a car going forward and backwards. It goes, it's,
Jesus took him 2 seconds.
yeah. Okay. And then what happens? Are we pretty sure that it definitely turns around and goes back that way?
Yeah.
Yes, we're certain. Why? Because we look at this graph and it's plus. We're also certain that it can, if there's nothing to stop it, it will go that way forever. Yep. Just depends on how much time you put in. It's not changing direction again. How do I know that? The graph.
Yeah.
It tells us. I'm following this motion here. It's always going to be positive. There's nothing to bring that down in the velocity function. And this as well, there's nothing to change that displacement.
We did it.
We've done it, yeah. And the final thing, find the total distance now it's traveled.
8. But first 3 seconds.
In the first 3 seconds.
Yeah, 8.
Yep.
4, 5, 6, 7, 8.
Wait, how'd you get it?
You counted 4.
We drew it. Yeah. 1, 2, 3, 4 this way. And I went 4 back. And this was 3 seconds, so we did it.
Oh, I see. What about 8?
Now, what about A? We did sign diagrams just by thinking here.
Yeah, right.
Like, this is a sign diagram. I'm not a fan of sign. They're okay, but it's better to look at the whole graph than a sign diagram. Oh, yeah. Okay, we could have done this for that. And you could have done the same thing for that's a sign diagram, just saying it's below the axis, it's above the axis. That's all it is. I prefer to look at the graphs and know the shape. So we'll ignore it. They'll never ask you to draw a sign diagram in an exam. They'll ask you just to interpret like this. They'll ask from question B on. All right, so I mightn't have put it up on ManageBack yet, but there is some homework. Not much. I don't think it's much. No.